Let us journey to perhaps the strangest place in the modern universe, a realm where matter exists in states you've likely never imagined. We're traveling to the interior of a neutron star, where the ordinary rules of physics bend into something altogether extraordinary. Neutron stars are what remain when massive stars die. When a giant star exhausts its fuel, when fusion finally stops and the outward pressure vanishes, gravity wins. The star's core collapses in on itself with such violence that electrons and protons merge into neutrons. An iron sphere the size of Earth compresses into a ball of pure nuclear matter the size of a city. The whole star implodes at 25% the speed of light, then rebounds in a supernova explosion that outshines entire galaxies. What's left behind is a neutron star, perhaps the most extreme object in the universe that isn't a black hole. These stellar remnants pack roughly 1 million times Earth's mass into a sphere only 25 kilometers wide. The density defies comprehension. All living humans would fit into 1 cubic centimeter of a neutron star matter. That's roughly 1 billion tons in a space the size of a sugar cube. Mount Everest compressed into a coffee cup. To explore such a place requires us to abandon the constraints of reality. No imaginable technology could withstand what we're about to experience, so we'll rely on pure thought, an indestructible craft immune to radiation and pressure, protected by fields that resist gravitational forces no human will ever encounter. As we approach, the first thing we meet is the magnetosphere. This is the strongest magnetic field in the universe. Even the weakest neutron star fields exceed Earth's by 1 billion times. But this isn't like the gentle magnetic bubble surrounding our planet. This space seethes with electrons and positrons, matter and antimatter pairs created from extreme energy photons in the magnetic field itself. The field becomes a particle accelerator, with electron currents flowing one direction and positron currents flowing the opposite, driven by their opposing charges. These particles blast outward along the magnetic poles, their motion creating the radiation we observe as pulsars, those perfect metronomes of the cosmos, spinning lighthouses that sweep space with beams of energy. Drawing closer, we notice something peculiar. The neutron star's surface appears fuzzy, softened by what could be called an atmosphere. Like Earth's atmosphere, this layer starts tenuous, almost vacuum, then thickens as we descend. But the similarities end there. Earth's atmosphere is nitrogen and oxygen in molecular form. The neutron star's atmosphere is plasma, atoms stripped of their electrons by extreme heat, around 1,000,000 Kelvin for young neutron stars. These nuclei are mostly hydrogen and helium, captured from the near-empty space surrounding the star. While Earth's atmosphere extends roughly 100 kilometers, the neutron star's atmosphere barely reaches a meter thick, with most plasma confined to a thin shell 10 centimeters above the surface. The difference? Gravity, crushing, incomprehensible gravity. When we land, our heads remain in the vacuum of space, while our feet rest in foggy plasma with density millions of times greater than anything on Earth. The gravitational pull measures roughly 100 billion times Earth's gravity. Here we encounter the first truly strange states of matter. The plasma beneath our feet resembles what's found inside white dwarfs, the dead cores of stars like our sun. The plasma is crushed so tightly that electrons approach overlapping. But quantum mechanics forbids this. Particles of the fermion family cannot occupy the same quantum state. The matter becomes what we call degenerate, and electron degeneracy pressure stops further collapse, ultimately holding the atmosphere up. Beneath us lies solid ground, a strange crystalline material. This seems peculiar because we normally think of crystals as lattices of atoms connected by electron bonds. But this substance is completely ionized, stripped of electrons. It's a frozen plasma with nuclei locked together in a regular lattice. You might wonder how nuclei can bind when they are all positively charged and should repel each other. At these densities, nuclei are pushed so close that their mutual repulsion actually prevents them from slipping past each other, like gridlocked traffic. The symmetry of that repulsion forces nuclei into a regular grid. This crystalline matter is mostly iron, the last element forged in the star's core in the hours before it exploded. Some of it still survives here at the surface. Now the real journey begins as we tunnel into the star's interior, entering the outer crust. Density increases with every meter. Suffusing the crystal lattice is a gas of electrons, a degenerate Fermi gas that holds this part of the star from further collapse. The deeper we go, the more energetic those electrons become. Soon, those energies drive exotic nuclear reactions. Electrons begin merging with iron nuclei in a process called electron capture. Negatively charged electrons combine with positively charged protons to produce neutrons. Iron converts into elements with fewer protons but equal mass, becoming extraordinarily neutron-rich. Several hundred meters down, At densities 50 billion times Earth's, we encounter nuclei that cannot exist anywhere else. Zinc 80, which would decay in half a second on Earth by ejecting neutrons, remains stable here, held together by incredible pressure and extreme electron energies. As we leave the outer crust for the inner crust, our nuclei become so neutron-rich they begin falling apart. We call this neutron drip. Neutrons leak from nuclei into the ever-narrowing space between them. This phenomenon begins about half a kilometer deep, at densities at least 1,000,000,000,000 times Earth's. We're beyond the point where particle accelerators can duplicate these conditions. We're relying on theoretical calculations, venturing into realms no laboratory has touched. As neutron drip intensifies, the space between nuclei fills with neutron gas. Meanwhile, the electron gas thins due to electron capture. The neutron gas starts taking over the electron's role. Neutrons are also fermions, so two cannot occupy the same state. The star becomes increasingly supported by neutron degeneracy pressure. But neutrons can get much closer before this pressure activates, allowing far higher densities. Further down, the nuclei themselves become fuzzy as protons are outnumbered by neutrons 5 to 1. A given neutron's wave function spreads so broadly that it becomes difficult to localize it to any particular nucleus. By the time we reach the bottom of the crust, around 1 kilometer deep, densities have reached 100 trillion times Earth's. The once distinct nuclei are beginning to touch. As we drop beneath the inner crust, things become properly strange. Welcome to the pasta, nuclear pasta. This is perhaps the least known and most peculiar state of matter in the universe. When nuclei start touching, they rearrange, forming exotic shapes. Nuclei face a competition. While neutrons and protons feel strong, short-ranged attraction due to the strong nuclear force, electric repulsion between remaining protons tries pushing them apart. Down here, with 20 neutrons for each proton, the protons cannot resist the forces reshaping the nuclei. The result is a complete rearrangement of matter. Nuclei reform radically, forming cylinders containing millions of protons and neutrons. Nuclear physicists affectionately call this phase spaghetti. At slightly higher densities, this nuclear spaghetti gets squeezed together to form sheets, nuclear lasagna. Because it's so dense, this material resists bending and movement. Nuclear pasta might be the strongest material in the universe, a quintillion times stronger than steel. The enormous strength of nuclear pasta allows it to resist gravitational forces and support texture. like nuclear pasta mountains buried beneath the surface. These could stand 10 centimeters tall, which sounds modest until you remember that every cubic centimeter weighs as much as an earthly mountain. As the neutron star rotates, these buried mountain ranges get dragged in circles, creating weak gravitational wave signals, continuous hums at exactly twice the star's rotation frequency. By the time we reach the bottom of the pasta layer, just above the core, all matter has been smooshed together into soup, mostly neutrons with occasional protons. The density is 200 trillion times anything found on Earth. And so we arrive at the core, where we find the most extreme conditions in the entire modern universe. Here, pairs of neutrons become connected to form Cooper pairs, which act as different particles. Some fermions effectively become bosons, which means they can do extraordinary things. Neutrons become a superfluid, a frictionless fluid that can sustain vortices with enormous energy. Some physicists think the dissipation of these vortices appears to us as glitches in pulsar frequencies. The rare Cooper pair protons turn the core into a superconductor, probably essential for maintaining the neutron star's enormous magnetic field. Approaching the dead center, even protons and neutrons begin losing structure and mushing together. This is highly theoretical, but extreme pressures and energies might create hyperon particles containing strange quarks. Or particles might not exist at all. Protons and neutrons might dissolve completely into quark-gluon plasma. While these plasmas have been created in Earth's collider experiments, we're not certain they exist in neutron stars. The only other time matter existed naturally in such conditions was within a fraction of a second of the Big Bang. If you are quiet, you might hear the faint booms of thermonuclear storms raging above us on the surface. Our neutron star has started accreting matter from a binary companion star. Its mass is growing, and at some point soon, it will form an inescapable event horizon. Will be trapped inside an actual black hole. Perhaps it's time to leave behind the strangest and most extreme place in all of spacetime. These bizarre objects aren't just theoretical curiosities. In August 2017, gravitational wave detectors picked up a signal lasting about 100 seconds, far longer than any previous detection. The signal was consistent with two merging neutron stars, 130 million light-years away. Around 2 seconds later, NASA's Fermi Gamma Ray Telescope identified a burst of gamma rays. For decades, gamma ray bursts were thought to come from neutron star mergers, but evidence was lacking. This event confirmed it. Optical telescopes located a bright spot in galaxy NGC 4993. You're seeing light from two neutron stars that merged 130 million years ago. The collision created a kilonova, spewing debris into space, debris containing heavy elements. New observations showed that gold, lead, and platinum were made in this event. This helps us understand where heavy elements in our universe come from. Think about that. Stars must die to create elements. They must die twice, once as a supernova creating neutron stars, then again as those neutron stars collide, forging the heaviest elements. Over millions of years, these atoms mix back into the galaxy. Some end up in clouds that gravity pulls together to form new stars and planets, repeating the cycle. Our solar system is one example. The remains of neutron stars that came before us are all around us. Our entire technological modern world was built from elements neutron stars made in eons past, sending atoms on a 13 billion year journey to come together and make us and our world. Neutron stars are cosmic ballerinas, spinning many times per second. When they first collapse, they spin extraordinarily fast, like a ballerina pulling her arms in. This creates pulses as their magnetic fields generate radio wave beams that pass every time they spin. About 2,000 radio pulsars are known in the Milky Way. The absolute best kind of neutron stars are those with companions, other neutron stars orbiting nearby. By radiating energy as gravitational waves, ripples in spacetime, their orbits decay. They spiral together, closer, until they crash and kill each other in a kilonova explosion. When they do, conditions become so extreme that heavy nuclei form again, not through fusion this time, but through heavy neutron-rich matter falling apart and reassembling. The two neutron stars collapse and become a black hole, dying yet again. From the outside, a neutron star is unbelievably extreme. Its gravity is the strongest outside black holes. If it were any denser, it would become one. Light bends around it, meaning you can see the front and parts of the back simultaneously. Surfaces reach 1,000,000 degrees Celsius, compared to a measly 6,000 degrees for our sun. These giant atomic nuclei exist because of a fragile balance that once defined their parent stars. Stars exist when the mass of plasma pulls inward through gravity, while fusion pushes outward. As long as this balance exists, stars remain stable. Eventually, in massive stars, iron forms. nuclear ash with no energy to give. Fusion stops. The balance ends. Without outward pressure, the core is crushed by the star's enormous weight above. Particles really don't want to be near each other, but the pressure is so great that electrons and protons merge into neutrons, which then squeeze together as tightly as atomic nuclei. The whole star implodes, bouncing off the iron core, producing a shock wave that explodes outward and catapults the star into space. This is what we call a supernova explosion. It will outshine entire galaxies. What remains is a neutron star, an object so strange, so extreme, that exploring its interior reveals states of matter existing nowhere else in the universe. From the crystalline iron surface to the nuclear pasta depths, from the superfluid core to the possible quark matter at the very center, these objects represent the universe at its most exotic. And perhaps most remarkable of all, the atoms forged in their violent deaths are the atoms that made you. Every element in your body, every gold atom in your jewelry, every uranium nucleus in Earth's core, all of it came from stars that died twice, from neutron stars that collided in catastrophic beauty, scattering their enriched ashes across the cosmos. We are quite literally made of neutron star dust. That connection across space and time, from the most extreme objects in the universe to the most ordinary matter in your hand, reveals something profound about our cosmic origin. We're not separate from these strange, distant phenomena. We're intimately connected to them, products of their violent creation, children of their spectacular deaths. The next time you hold something made of gold or platinum, remember its origin. Those atoms were forged in conditions so extreme they exist nowhere else in the modern universe except in the hearts of colliding neutron stars. And that makes even the smallest piece of matter extraordinary.